In this video, we're going to learn about redox reactions, and we'll learn how to balance redox reactions and explore a variety of different reactions. So first of all, we need to know how to balance a redox reaction in an acidic solution. So first thing you need to do is you need to figure out what is being oxidized and what is being reduced, and you do that by using the oxidation states. Then you balance the atoms, everything except for hydrogen and oxygen. And then you balance the oxygen by adding water on the side that has the less oxygen. And you balance for hydrogen by adding protons on the side with less hydrogen. Then you add electrons on the side that's more positive to balance out the half reactions. And then you balance each half reaction for electrons. And then finally you combine the half reactions and cross off the items that repeat on both sides. So there's quite a few steps for these ones. So the example we're going to explore says permanganate ions, MnO4-, react with iron 2+ ions in acidic solution to form manganese 2+ ions, iron 3+ ions, and water. So first thing we need to do is decide what's being oxidized and what's being reduced using the oxidation states. So first of all, the iron ions are being oxidized to form iron 3 ions. And that's because there's an increase in the oxidation state from +2 to +3. So we're going from Fe2+, and it's becoming Fe3+. So that one was easy enough. It said right in the equation that it was being oxidized. So that's the first one. The second one's a little trickier, but we can figure it out. So we've got MnO4-. So remember, we need to figure out what the oxidation state of manganese is in the example. So remember, it'll be Mn plus 4 times O equals -1. So remember that the oxidation state for oxygen and compounds is -2. So it's going to be Mn minus 8 equals -1. So we transfer the 8 minus 8 over. So the oxidation state for manganese is +7 in the permanganate ion. So because it's going from +7 and we're told that it's becoming 2+, it's a decrease in the oxidation state from 7 to +2. So that's the one that's being reduced. So this one's oxidized. And then MnO4- is becoming Mn2+. So that one's being reduced because it's going from +7 to +2. So the next step we're to do is to balance for atoms other than hydrogen or oxygen. So they're already balanced. So we have our Fe2+ to Fe3+. So that one's already balanced for iron atoms. And then we have MnO4- becoming Mn2+. So that one's already balanced for manganese atoms as well. But now we need to balance for oxygen by adding water to the side that has fewer oxygen atoms. So in this case, we need to balance this one. So MnO4- goes to manganese 2+, aqueous. But we need to take care of the oxygens. So we need 4 oxygens, so that means we need to add 4 water molecules, like so. Now we need to balance for hydrogen by adding hydrogen ions to the side that has the fewer hydrogen atoms. So if we rewrite what we have from our last bit, So MnO4 aqueous becomes Mn2 plus aqueous plus 4 water molecules. We now know that we need to add, there's 8 hydrogens involved in those 4 water molecules, so we have to add 8 hydrogen ions or 8 protons on the left-hand side. So that's taken care of. So now we need to balance each half equation for charge by adding electrons to the more positive side. So we need to go back to the iron. So we have Fe2 plus aqueous makes Fe3 plus aqueous, and we have 1 more electron on the 2 plus side than the 3 plus side, so we just need to add an electron there. And then on the other one, we need to figure out how many electrons we need. So we have our H plus aqueous plus MnO4 minus aqueous makes Mn2 plus aqueous plus 4 H2O liquid. So now, if you take a look, we have on one side a +2 charge, and right now on the other side we have the 8 hydrogens that are positive hydrogen ions plus 1 negative ion, so we have 7. So it's a +7 on one side, but we need to balance it both sides, so we need to add 5 electrons on this side, like so. So our next step is to balance the 2 half equations for electrons. So we have 5 electrons on the manganese reaction side. So we need to put 5 electrons over here. But because we do that, we need to account for the electrons with the positive ions. So we now need to balance out what's being lost and gained. So if there's 5 electrons on the manganese side, that means that we need to have 5 here and 5 here, because we have to have the positive charges balance out as well. So now we need to cancel out what appears on both sides of the arrow to get the overall equation. So we can see that the 5 electrons, if we erase that and erase that, now we'll combine the 2 reactions and rewrite. So we have 5 Fe2 plus aqueous plus 8 hydrogen ions aqueous plus MnO4 minus aqueous becomes 5 Fe3 plus aqueous plus Mn2 plus aqueous plus 4 water liquid. So there's our balanced equation. So the Winkler method is a redox reaction that's used to determine the amount of dissolved oxygen that's in water. It's also used to find the BOD, or the biological oxygen demand, for water samples. So BOD is the amount of oxygen that's needed to decompose organic material in a water sample over 5 days. So if the BOD is high, the sample is polluted and will be prone to algal blooms through the process of eutrophication, which you probably learned about in biology class. So to be able to find the biological oxygen demand, you first saturate the water sample with oxygen so that the concentration of oxygen is known, and then you incubate the sample in the dark at a fixed temperature for 5 days. The microorganisms that are present will oxidize the water sample. And then you do a variety of redox reactions to calculate the biological oxygen demand. So this is an example here. So you fill your water bottle with the field sample. You add some manganese sulfate. You add some alkali iodide azahide, which some of these compounds are toxic, so we don't normally use them in our science labs. You replace the stopper, you shake it, and then you add sulfuric acid, replace the stopper and shake again. Then you titrate out some of the sample and then add a starch indicator, and then you titrate the sample until it's clear. So it's a very complicated process, but it is a way of finding out how much oxygen is being consumed by the microorganisms. So on an IV assessment, you do need to know the reactions that are involved. So they're listed here, but Cognity gives a really helpful hint. What you do need to remember, because the reactions are so complicated, you need to know the molar ratios that are reacting. So if you take a look at each of those reactions, 1 mole of oxygen interacts with 2 moles of iodine, which interact with 4 moles of S2O3 2-. So that's the ratio you need to know. That is a 1 to 2 to 4 for oxygen, iodine, and then S2O3 2-. And that's all you'll need to do for a question on a potential assessment. There is a good video explaining the Winkler method more in depth through Richard Thornley's videos, so you might want to look that up, the Winkler method, so you can get an understanding of what the process of those reactions, so you can understand it a little bit more. So we're going to be doing an example that's taken from Cognity, trying those reactions, remembering those molar ratios. Remember, 1 oxygen to 2 iodine to 4 of the S2O3. So here is the example. To measure the BOD of a river, 2 300 centimeters cube samples of river water were collected. So that's 300 milliliters. The Winkler method was used to determine the initial concentration of dissolved oxygen in one sample at day 0. Then 30 centimeters cubed of 0.01 moles per liter of Na2S2O3 was required to reach the endpoint of the titration. So they did a titration and found out that's how much they needed. The second sample was then stored in a dark place to be tested after 5 days. So we're being asked to find the initial concentration of oxygen and then to find the BOD if after 5 days the sample contained 1.88 times 10 to the negative 5 moles of oxygen. So the first thing we need to do is set up our handy stoichiometry table. On one side we'll be working through the concentrations to find the moles in the ratio. On the other side we'll be working back up to find the mass in milligrams, because we're going to find out how many milligrams per liter, because that will tell us the parts per million. So often when we're talking about really small concentrations of things, we do them in parts per million, and that's what we'll do here especially when we're talking about pollution. So the first thing we're going to do is we're going to put our species at the top, so the things that we're calculating. So we have S2O3 and then O2. Remember that the ratios are 4 to 1. So we have, for every mole of oxygen, you need 4 moles of S2O3. So we have our concentration, our volume, our moles, our ratio on that side. Remember, concentration times volume will give us our moles, and then we'll divide down to get and multiply up to get our moles of oxygen. So we have concentration of 0.0100 moles per decimeter cubed as our concentration, and we had 30 milliliters or 30 centimeters cubed we need to divide that by 1,000 to get our actual amount. So it's 3.00 times 10 to the negative 4. So that times that will give us our number of moles. So we have 3.00 times 10 to the negative 4 moles of the substance. Now we need to divide by 4 and multiply by 1 to get our number of moles of oxygen. So that's going to be 7.50 times 10 to the negative 5 moles. So now we need to convert from that to our mass in milligrams. So we need to know the molar mass. So remember, when we're working with mass relationships, you multiply up the column. It just gets wonky when you're talking about concentrations. So we need to know the molar mass of oxygen. So it's 2 times 16.00, which is equal to 32 grams per mole. But in this case, we are converting to milligrams. So we'll do our calculation, 7.5 times 10 to the negative 5 times 32. But then we're going to times by 1,000 to get the number of milligrams. So it is 2.40 milligrams. However, we're not quite finished because we need to find the concentration of the O2. So we need to remember how much we had originally. So it's 2.40 milligrams in 300 milliliters, or 0.300 liters. So that's going to be equal to 8.00 milligrams per liter, which is also equal to 8.00 parts per million. So there's our concentration of oxygen. So now we need to find the BOD. So for this one, we were given the final amount of dissolved oxygen. So after 5 days, there was 1.88 times 10 to the negative 5 moles. We were given that in the original problem. So the first thing we need to do is convert that to mass. So we need to multiply that by the molar mass to get our number of moles. We'll also multiply it by 1,000 to get it in milligrams. So we're going to do 1.88 times 10 to the negative 5 moles times 32.00 grams per mole, because that's the molar mass of oxygen. And we're going to times it by 1,000 to get a value in milligrams. 0.602 milligrams. Now we need to use the concentration formula to figure out how much is in there after the 5 days in concentration in parts per million. So now we take our mass. So the concentration of oxygen is equal to the mass over the volume, because this is a mass volume concentration. So that's going to be equal to 0.602 milligrams over, remember it's 300 milliliters, so that's 0.300 liters. That's going to be equal to 2.01 milliliters, or milligrams per liter. So now we can figure out how much the oxygen demand was. So how much was left after the 5, or how much got used up over the 5 days. So the BOD is equal to our original, so 8 milligrams, or 8 parts per million, sorry, minus 2.01 parts per million. And that's equal to 5.99 parts per million. So that would be the BOD. So redox titrations are titrations that involve a redox reaction. One example is to determine the amount of iron in supplements or in different foods. So the first thing, if you were doing it with a supplement, you would dissolve the iron in acid to convert the iron to Fe2+. Then you'll titrate the solution with an oxidizing agent. Potassium permanganate is one, or you could use potassium dichromate. In this titration, the Fe2+ will be oxidized to Fe3+, and the endpoint will be determined when the purple manganate 7 ions are reduced to become manganate 2 ions. So we get a nice color change from purple to transparent. So the reaction is 5 Fe2 plus the permanganate plus 8 hydrogen ions makes the manganate ion Mn2 plus 5 iron 3 plus 4 water. So this is the actual redox reaction that we balanced in our first bit of the video. So in this example, also taken from Cognity, a student carried out an experiment to determine the mass of iron in an iron tablet. The iron tablet, with a mass of 1.000 grams, was first dissolved in an acidic solution, and the iron was converted to iron 2 ions. The resulting solution was then titrated with a 0.1 mole per liter solution of potassium permanganate. The average volume of potassium permanganate needed to react with the iron 2 plus ions was 22.4 centimeters cubed, or 22.4 milliliters. Determine the mass of iron in the iron tablet. So to find the number of moles, we would use our C equals N over V, so N equals C times V. We were told that the concentration was 0.100 moles per liter, and our volume is going to be 0.02240 milliliters, or liters, sorry, we converted it, so we had to divide by 1,000. And then when we multiply that, we get a number of moles is 2.24 times 10 to the negative 3 moles. Now that we have that value, we can solve to find out the mass of iron. So now we can take our information and find out how many moles, or what mass of iron we have, using stoichiometry again. So we know the number of moles of potassium permanganate, but we need to remember the balanced chemical equation. So remember, from the balanced chemical equation, we have 5 iron ions for every 1 mole of permanganate. So we now need to put in our number of moles. So we had 2.24 times 10 to the negative 3 moles. We need to divide by 1, multiply by 5, so we actually have 0.112 moles of iron 2 plus. Now we can determine the mass by multiplying that value by the molar mass of iron, so 55.85 grams per mole. So we have 0.626 grams of iron in the tablet.